In this video, we are tasked to identify the points of discontinuity for our given function f of z is equal to secant z. Take note there are no given values for z to try on as to whether this is continuous at a certain point, unlike the previous examples that we had. But this time we just simply ask about the points of discontinuity. It will be the value for a z where when used for this given function will be undefined. So since this is secant z, and again there's no specific interval for that, so we are asked to identify all possible values for our z here. Now, how do we show those points of discontinuity? Now, it may be very difficult for us to look into secant itself, so why not try to convert it into an equivalent form using cosine or sine, or probably both of them. But we know that our secant z is equivalent to 1 over cosine z. Okay? We know that to be the equivalent form for trigonometric functions, which is also true for complex numbers. Now this time, we have noticed that our secant z is now transformed into a rational expression or function where our cosine z is at the denominator. When can we say that this given expression 1 over cosine z is undefined? Because that's our goal, the point of discontinuity. So this is only true, or we can identify the values for which 1 over cosine z is undefined, or secant z in the original form, if this denominator is equal to 0, which is the cosine z is equal to 0. So we can only say it here. We're going to show the values for z for cosine is 0. Okay, so let's talk about our Cartesian plane, or I mean the unit circle. What would be the value of this z? Take note that z is a complex number, so it could be a real value only, or a value with imaginary unit, or a combination of both. So when is this true? Take note in the Cartesian plane, this is true if our value for z, which is the angle, and let's just simply talk about the simplest form, cosine theta be equal to 0, just like in the real numbers. So this is only true if we have here pi halves, or 90 degrees, because the value for the pi halves, or its coordinates, is actually 0 and 1, and the cosine, which is the x, is actually equal to 0 at pi halves. But take note, there's no, again, boundary for this. So when we look at the possible value for this, is actually including 3 pi over 2. In our unit circle, pi halves is here, 3 pi over 2 is here. As we look into its rotation, so it's also another value for theta. Now this is also true for our z here. Our z, which also considered as an angle in this case, could also take the value of pi halves and 3 pi over 2. Okay? These are the two possible points of discontinuity for the given function, because if this would be plugged in here, it will actually make the entire denominator 0, therefore the function is discontinuous. Again, take note we don't have any interval. What's the point here? We don't have any interval. That would mean we can also include all the coterminal angles of pi halves and 3 pi over 2. Talking about moving here as well. We also pass to this point, but it's no longer pi halves. It's a coterminal angle. Okay, by one revolution. So revolution. So it includes another pi. Okay, so pi over 2 plus, it's not pi, plus 2 pi, because it's one revolution. Okay, so it's like that. Similarly, that's actually, this is actually for pi over 2. Now for 3 pi over 2, the same thing, one revolution for that here, we will have another value of 3 pi over 2 plus another 2 pi. And again, it doesn't have any interval limitations or boundary, so we can even add additional boundaries for that, so on and so forth. We are asked about the points of discontinuity. We don't have any interval, so we need to include all of them. How can we write all of this to get this one here together with this value to represent the values of z? Now, it's very simple to look at. Take note that actually, when you move from here to there, 3 pi over 2 is just pi halves plus a certain pi. Okay? One of its coterminal angle is with 2 pi. And since 3 pi over 2 is this is just pi over 2 plus pi plus 2 pi, which is that one. So we have here 3 pi, or pi over 2 plus 3 pi. You can see that this value here increased by pi, and pi by integral values. So in generalization, we have here the values for z for the points of discontinuity for the given trigonometric function is actually pi over 2, okay, plus you can actually use k pi for all k element of integers, okay, element of integers, because if you're going to use here 0, so we have pi over 2. If we're going to use here 1, that's 3 pi over 2. 2 is the coterminal angle of pi over 2, and so on and so forth. Even if we're going to use negatives, take note that for unit circle, we can also have a value for our angles in its reverse order. So the negative will have minus. So this being pi over 2 will also be equivalent to this, which is negative 3 pi over 2, when you will have pi over 2 minus pi. So this is actually 2 minus 2 pi. So that's actually negative 3 pi over 2. So we include negative values for k. That's why we have this. So just to emphasize this is our final result for the points of discontinuity of our given trigonometric function. Again, this is possible because our z here is actually expressed as an angle of cosine, or generally an angle of your secant. Thank you very much for watching.